projects. In this video, we are going to explain about the project entitled as Urban Parking Demand Forecasting using XLSTM Informer Model. So before getting into the video, let me give you the brief explanation about the project. The project focuses on predicting future parking availability in smart cities using advanced deep learning techniques. The model combines XLSTM's enhanced memory capability with Informer's efficient attenuation mechanism to capture both short-term patterns and long-term trends in parking data. This approach helps reduce traffic congestion, improve parking utilization, and support intelligent urban mobility solutions. Coming to the abstract, this abstract explains the importance and motivation behind the proposed work and how it addresses existing challenges. It begins by highlighting that accurate urban parking demand forecasting is crucial for smart cities as it helps reduce traffic congestion, decrease the time drivers spend searching for parking, and ensure better usage for available parking spaces. It then points out the limitations of traditional forecasting methods, which often fails to effectively model complex time-based patterns and long-term dependencies found in real-world parking data. To overcome these issues, the work introduced an XLSTM Informer model, which integrates the strong temporal memory capabilities of XLSTM with the efficient attenuation mechanism of the Informer architecture. This combination enables the model to handle large-scale time series data more effectively while delivering higher prediction accuracy and better scalability, making it suitable for particular smart parking applications. Coming to the existing system, this existing system describes the limitations of current parking demand forecasting methods. Existing system commonly uses statistical techniques like arrhythmia and regression, along with traditional machine learning and deep learning models such as LSTM and GRU to predict parking demand. Although these approaches are effective in capturing short-term trends in time series data, they struggle with modeling long-term dependencies and complex temporal patterns found in urban environments. Additionally, as the size and dimensionality of parking dataset increases, these methods require higher computational resources and their prediction accuracy decreases. Consequently, their overall performance becomes less reliable in dynamic and large-scale urban parking scenarios. Coming to the proposed system or base paper work, this proposed system explains how the proposed system improves parking demand forecasting. The system is built using a hybrid XLSTM Informer model designed to address the shortcomings of traditional forecasting approaches. The Informer component efficiently captures long-term dependencies in large time series datasets through a spare self-attenuation mechanism, reducing computational complexity. At the same time, XLSTM strengthens memory representation and extracts meaningful temporal features from parking data. By combining these strengths, the proposed system delivers accurate, scalable, and reliable parking demand predictions, enabling real-time smart parking management, reducing traffic congestion, improving parking space utilization, and enhancing overall urban mobility. Coming to the dataset, this dataset provides detailed and real-time information collected from IoT-based smart parking systems, making it highly suitable for parking demand analysis and prediction. It contains time-stamped records for individual parking spots, including occupancy status, entry and exit times, and parking duration, which helps in understanding parking usage patterns over time. In addition to parking activity, the dataset includes vehicle details, payment status, and sensor data from technologies such as ultrasonic or pressure sensors. It also incorporates contextual factors like weather conditions and nearby traffic levels, along with parking lot characteristics such as zone, spot size, EV charging availability, and user type. Due to its rich and diverse features spanning multiple years, the dataset is well suited for training advanced forecasting models and supporting efficient data-driven smart parking management and urban mobility solutions. Coming to the novelty or extension or enhancement or improvement. This study introduced several key extensions compared to the base paper. Unlike the original research, which forecasted both parking entry and exit, our work focuses slowly on enter forecasting due to dataset limitations, achieving improved performance with a bi-LSTM model. In addition, we incorporated explainable AI techniques including line and shape to provide insights into feature importance and enhance the interpretability of the model prediction. Furthermore, we developed a Flask-based user interface enabling users to input data and obtain real-time predictions from the trained models, making the system more interactive and practical for deployment. These extensions collectively enhance the accuracy, interpretability, and usability of parking demand forecasting compared to the base study. Coming to the flow of the work, first we need to import the packages. All necessary Python libraries were imported to handle data manipulation, time series forecasting, deep learning models, visualization, and explainable AI techniques. This ensures the workflow can support both standard models and advanced extensions like bi-LSTM and XAI methods. Next, exploring the dataset. The smart parking management dataset was loaded and explored to understand its structure, distribution, and features. The steps allowed identification of important attributes relevant to enter forecasting, which is a main focus due to the unavailability of exact data. Next, pre-processing. The dataset was resampled into hourly intervals to standardize the time series data, which is crucial for accurate forecasting. Feature engineering was performed to create additional variables such as time of day indicators and rolling averages, which enhance model learning and prediction accuracy. Next, normalization. All features were scaled using Minimax scaler, ensuring that values are within a standard range. This step is particularly important for deep learning models like LSTM, bi-LSTM, and transformers, as it prevents large numerical differences from destabilizing the training process. Next, train test split. The dataset was divided into training and testing subsets to allow unbiased evaluation of model performance. This step also ensures a fair comparison between multiple models, including both base and extension models. Next, build models with hyperparameters. Multiple models were implemented including LSTM, XLSTM, Informer, Transformer, Autoformer, XLSTM Informer, and Aremia to provide a comprehensive benchmark framework. And as an extension, a bi-LSTM model with multi-horizon forecasting was developed. This model can predict multiple future time steps simultaneously, which increases its practical usefulness of urban parking demand management. Next, model evaluation. All the models were evaluated using MAE, RMSE, MAPE, R-square, and training time, providing a throughout assessment of both accuracy and efficiency. This is an extension beyond the base paper, which reported limited metrics, enabling a better understanding of the trade-off between model complexity and performance. Next, visualization or comparison of graphs. Comparison graphs were generated to represent the performance of each model across multiple metrics. This extension helps stakeholders quickly identify the best performing model and understand differences between models at a glance. Next, save the best trained model. The best performing model was saved using joblib, allowing it to be reused for predictions in a real-time environment. This step is essential for integrating the model with the front-end interface. And next, explainable AI techniques. Lime and SHAP were applied to explain feature importance and the contribution of each input to the final prediction. This extension improves transparency and helps users and stakeholders trust the model, which is particularly important for complex deep learning models like bi-LSTM. Coming to the front end, a user interface was developed using Flask framework which includes registration and logging functionalities supported by an SQLite database. This ensures secure access for users and allows the system to be deployed as a practical web application. The front end allows users to input custom feature values for prediction. This extends the system's usability, allowing real-world application rather than just offline model testing. The user provided input is pre-processed in the same way as the training data, including feature scaling and any necessary transformations. This ensures that the model can make accurate predictions using the real-time input. The saved by LSTM or best performing model is used to generate predictions based on the pre-processed input. This extension allows the system to provide real-time, actionable forecasts for parking demand. The prediction results are displayed on the front end in a clear and user-friendly format. This extension improves accessibility and enables decision makers or users to understand and act on the forecasted parking demand. Coming to the algorithms used in the project are LSTM, XLSTM, Informer, Transformer, Autoformer, XLSTM with Informer, Arrhenia, and as an extension we have used by LSTM with multi-horizon. Coming to the requirements, we have both hardware requirements and software requirements. Hardware requirements consisting of operating systems, Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements consisting of application framework is Anaconda, primary language is Python, front-end framework is Flask, backend is Jupyter Notebook, database is SQLite 3, technologies which we use to build the front-end are HTML, CSS, JavaScript and Bootstrap 4. To execute the project first, you need to open the code folder which contains source code files. This folder is a complete package of your project's code base containing everything needed to develop, test and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represents different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as pre-processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are the model files which contain algorithm information which will be loaded into the project code during the runtime. Notebook.ipynb file. This is a Jupyter Notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. Signup.db file. This file is a database file used to store the user information. Now, coming to the execution of the project, first, you need to copy the path of the code folder from the address bar of the file explorer. Then, open Anaconda prompt. Using the command cd followed by a space, and then paste the copied path. This command is used to change the current directory to the code folder's path. Now, compile the app.py file using the command python space app.py in the Anaconda prompt. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address with a port number of 5000. Copy the local link provided by the framework and paste it into any web browser. I prefer Chrome. So this is the homepage of the project should now be displayed in the browser. This is a front-end built using Flask framework. In this page, we have Home button and Sign Up button. Firstly, click on Sign Up button so that the log on HTML will be opened. Here, we need to give the details and create an account for user authentication like username, full name, mail ID, mobile number, and a strong password. Then click on Sign Up so that all the given details are stored in signup.db and the login.html will be opened. where you need to access the application by username and password. Then click on login so that the prediction page has been displayed. In this page, we have prediction button, graphs button, notebook button and sign out button. Firstly, click on prediction button so that the parking demand forecasting form will be opened, where you need to upload the parking data and select a forecasting horizon to predict future demand. Firstly, let us choose the file. Now, select the forecast horizon. Then click on run forecast so that the input will be pre-processed and the output will be displayed as forecasting results for 1 hour ahead. It's given historical actual versus forecasting graph and future forecasting graph along with recent historical window. Here we have timestamp, temperature, visibility, hours in, hour cost, dows in, dow cost is weekend, entry lag 1, entry lag 24, enroll 3. And we have future forecasting like timestamp and forecast. And next, click on new prediction so that the form will be opened where you can enter the other CSV file and check for future forecasting. Now, click on graphs so that the graphical representation of the projects will be opened. So let us check one by one. First, we have RMSE graph. The graph compares the RMSE, which means root mean squared error of different forecasting models where lower values indicates better performance. Most deep learning models achieve low RMSE, showing strong predictive accuracy. Aremia has a much higher RMSE, indicating significantly poorer performance compared to the others. Overall, Autoformer and BiLSTM appear to be among the best performing models. Next, we have MAE graph. The graph shows the MAE of different models where lower value indicates better accuracy. Deep learning models such as Autoformer, BiLSTM, and XLSTM achieves the lowest MAE values. Aremia has significantly higher MAE, indicating weaker predictive performance. Overall, modern neural network based models outperform the traditional Aremia approach. Next, we have MAPE graph. The graph compares models using MAPE where lower values indicates better relative accuracy. Transformer based and BiLSTM models achieve the lowest MAPE, showing strong performance. Aremia stands out with a very high MAPE, indicating poor percentage-based prediction accuracy. Overall, deep learning models significantly outperform the traditional Aremia model. Next, we have R-square score graph. The graph compares R-square scores of different machine learning models, showing how well each model explains the variance in the data. The transformer model performs best by large margin, indicating superior predictive capability. Most other models have low but positive R-square scores, meaning limited explanatory power. The Aremia model has a negative R-square, suggesting it performs worse than a simple baseline. Next, we have time trained by model graph. The graph shows the training time required by each machine learning model. BiLSTM models take the longest time, indicating high computational cost. Aremia is the fastest to train, requiring minimal time compared to deep learning models. Most transformers and LSTM based models have moderate training times in comparison. Next, we have explainable AI SHAP graph. The SHAP summary plot shows how each feature influences the model's prediction. Features at the top have the greatest impact on the output. Points to the right increase prediction, while points on the left decrease them. Color indicates feature values like red equals to high values, blue equals to low values, showing how value magnitude affects impact. Then click on sign out so that the project demonstrates that the hybrid XLSTM informer model along with the BiLSTM extension can accurately forecast urban parking demand, providing reliable predictions for entry data. The integration of explainable AI enhances model transparency, while the Flask-based front-end makes the system interactive and practical for real-world use. Overall, This approach offers a scalable, interpretable, and deployable solutions for efficient urban parking management. So this is all about your project. Thank you.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.